Hey guys, how's it going? Welcome to another episode of Ferris Makes Hardware. We're already to our 5th episode of this. This has been going so fast. Um, so I'm pretty excited about this. Hold on, I got some floaty windows. Anyway, gonna be continuing on xenowing today. Not gonna be nearly as long stream as long of a stream as last weekend. For those of you guys that didn't catch Thursday's stream, we made it a bit far in terms of improving our design. Let me pull up the current net list, which looks a lot better than it did. However, there's definitely ways that we can improve this more. Here we go. Give Cordis a minute. Come on. There we go. And our netlist viewer. All right. So basically what we did last episode is the CPU was working already, but now there's a lot of ways that we can simplify it. And I would like to explore a lot of those before I move on, just while it's fresh in my head. Although we're not going to go too far with this, just a couple optimizations and some simplifications, and then I'm going to be done with it for now. But particularly, we got the CPU to be a lot simpler, particularly the register file. This actually exploded the way that we were reading and writing registers before. Now it looks somewhat sane, but it seems that we can actually still improve this quite a bit from where it is now. It's still making this big register file out of muxes and flip-flops, which, while that's not terrible in and of itself, we should be trying to get the compiler to use a block RAM here. So yeah, this is quite a bit nicer than it started out on the stream the other day. So I'm pretty happy with the progress so far. It just was pointed out to me that we can do better. So looking forward to trying to do that. I wanted to check. I want to just run this through the entire flow again, because I want to do what we did before, where we did like a resource utilization, just some numbers before and after. This will be, again, fairly unscientific and straightforward. I changed my tunes. Bloop. The main thing we changed was we changed some of the access patterns here. Let me bump this up for you. We changed some of the access patterns to the registers themselves. So before I was doing this regs thing with the entire file, and then I would do a regs next with this whole file again, and then have that feedback, and then update small parts of it. But that the compiler didn't seem to really like that I was doing that. First of all, because we had some offsets in there, and now I actually model even register 0 as an actual register, and just make sure to keep its value at 0 by not writing it. So basically move the writes down to here so that they're always synchronous. So we have a write enable, and then it will always write to RD as long as it's not 0. And because it's only writing here, it was able to simplify that graph quite a bit. And the next thing I'm going to do is I'm actually going to refactor reads to basically do the same thing as well, and see if I can simplify that even more. And if the reads are synchronous like this and the writes are also synchronous, it should be possible to get this to infer a block RAM. So I'm pretty happy about that. Well, if it works. By the way, I'll say hi to guys in the chat really quick while we're waiting. Mortar A, Free Full Zoc War, Daniel Collin, Pyro ESP, and Creekpot. How's it going, guys? Daniel Collin, have you thought much about adding some integer SIMD ops, or do you plan to keep the CPU as simple as possible? Right now, I'm just going to keep it as simple as possible. I think it's... Hey, love like Semtex. Good to see you, man. Yeah, right now I'm going to keep it as simple as possible. I want to get it just to the point where it's working and running C code, basically. And at that point, I want to start focusing on like the rasterizer and getting those up to speed as well. Because I want to get all that stuff to work and then start optimizing where the big pain points are. Hey, Gravish. Yeah, that's probably a good idea as well. And it'll probably be a lot more natural to do that as well after refactoring this a bit too. So yeah. Anyway, what I wanted to take note of is these here, these numbers here. So LE's 6520 and regs 4503. Those numbers should both go down. And then memory bits is already kind of high. I don't really care about taking that number. A lot of this is from signal tap as well, which I still want to keep in there just to see that we're using that. Actually, it's probably interesting to disable that just to get more clean numbers, because it's not terribly hard to re-enable that. It just takes a minute because I have to recompile everything. I'm actually going to do that. Turn on my FPGA while I'm at it. Freefall, how much of this is inspired by the thing LFT made for his parallelogram demo? This wasn't actually inspired by that initially. It was more that a buddy of mine wanted to do like his own handheld based on 3D printing a case around and designing some peripherals for Raspberry Pi. And I was like, you know what? I've always wanted to make my own handheld. Why don't I do it on FPGA? Although I do love LFT's parallelogram demo. This actually wasn't inspired by that. At least not initially. I have been watching it a bunch recently because I do think it's inspiring now, but yeah. Whoops, where'd my stuff go? There's that window. Yeah, as you can see, the logic elements go down a lot, and especially the memory bits go down quite a bit. Because it doesn't have to use so much internal storage to store all the capture data. Compilation should be a little bit faster too. I like using signal tap just to make sure things are working as I expect right now, though, because we are still so blind. But this will give us better numbers, so I think it's a kind of a better starting point. Looks like it goes down a little further too after like placing a route and stuff. It's funny too that it has 5 pins, but that's clock, reset, LEDs, and that's all it has in this design right now. Looks to be fine on the hardware. So yeah, so we're actually going to start at 3029 and 1347 registers, and I will actually write down the memory bits. 131072. So here's our before numbers. Nice and easy. And then yeah, we'll check this stuff out. I was going to run this in the simulator, although that should be exactly the same. Cool. So, yeah, the biggest thing is that I want to refactor. So we do writes enabled like this, which will only write synchronously. Technically, I think I am still reading this relatively synchronously because the values are only read. Like, I get the values combinationally. They're here. And the inputs to all these, RS1 and RS2, end up being synchronous enough signals, basically. But yeah, they're... I think just because this is not... Like, the compiler is not really smart enough to understand that the things that this depends on only changes synchronously. I think it just assumes it's combinational, and so then it has to build the memory combinationally, assuming that any of its inputs can change and any of its outputs can change. And that's why you have this whole register mux setup. So, not ideal, but if we're able to change this, I think we'll be pretty good. A couple things here. The first thing is that if we look at the states of the CPU, we have an instruction fetch state, and basically all that's really doing is just waiting for the data to be ready, and when it is ready, we're just going to read in the data into our instruction register, and then go to our decode state. And the decode state is kind of a decode and execute state compared to a lot of other processors, just because it can be. All of this is combinational. But we're probably going to have to split decode into 2 stages. We're going to do one that's going to read the registers based on the value of the instruction. And then we're going to do another one that's actually the execute state. Probably we can simplify that, but I think that's the easiest way to move forward from where we are now. And that way, these RS1 values and RS2 value things here, these are going to end up being, these values here are going to end up being read synchronously between the two states. And then we'll have those ready for basically the same logic that we have here. And we might also be able to do this ALU, LHS, and RHS stuff a little bit differently, but we'll have to see. We may not have to. So all in all, it gets pretty simple. We just have to split out another state. That will make things a tiny bit slower, but I think that will make it simpler. So let's do that. This shouldn't be too hard to do at all. We should just be able to add another state here. State execute. I might even call this state RAID register read, just to be really explicit, because that mirrors our write back pretty closely. Should probably also move this into system verilog enum as well, but I don't really care that much right now. So then, actually, where this is going to be, it actually comes here. So maybe we call this, maybe we still call this decode and execute. Yeah, let's do that. Yeah, I'll definitely consider that, Grave Wish. I mean, it makes definitely the individual elements simpler, but I'm not sure if it makes seeing the sequentiality between them simpler. So I think it's worth trying both and seeing which one I like better, to be honest. But I do think it would help the compiler, though. That's definitely a good point. Even if I'm not doing the pipelining. Because, I mean, the benefit there, the reason I'm not doing the pipelining is because I don't want to do the hazard detection and or response to hazards either. Basically just want to avoid hazards entirely. But if I had these in the separate units and I'm going to run through that amount of states anyway, then it probably could make a lot of sense. But yeah, we'll get there. So I'm actually just going to rename this state to, or we'll do this. This will be the execute state now. And we'll do that, set up our next state, and then here, I think all I'm going to do is just set up the reads. So we may not actually need another state for this, but we'll do it anyway. We'll make it simple. Yeah, just like we had with our, had an RD enable here and an RD write value. And I think we're gonna do something very similar to that here. So these here, RS1 value and RS2 value. I'm gonna do this. I think did I handle these on reset? Because I probably should be doing that. Even though those end up being combinational signals, is probably why I don't do that. But the RS1 value will need to be. This would be 0 on reset. Otherwise, then we can do rs1 value, read that in from our rs1, rs2 value, regs rs2. So it should be able with this to infer that it just needs a synchronous RAM with 2 read ports. We should be okay with that. The read enable signal itself is, of course, just going to be a continuous signal. Or a combinational signal. So, had that there. We'll do this. So normally it's going to be 0. But here. I think if we just do this, it'll more or less work as we expect already. So I'm just going to try that in our simulator now. And so far it didn't work. And that's probably because it's not moving to the next state. Yeah, so we got a fewer of these LEDs change messages than we had last time, and that's because everything's going to run slower. Basically, every instruction is going to take one more cycle now, and that's okay. Looks to be behaving correctly at least. Hey, Gamer Steve, I'm not making a game right now. I'm making a game console, and there's no software for this yet other than some LED stuff. So I can't really have that. I don't really have a good answer for that. So yeah, this seems to work. I also am going to compile this on the hardware. And this should hopefully show us something simpler. And we got some errors. 587. Okay, apparently it needs the specifier here. That's annoying. Again, test here because it's faster. Of course, that still works. And we'll test here. Hey, G Superland. Yeah, I actually do think writing emulator for this would be a fun project. It would be kind of cool to see the different things side by side. It would also be a really good project to do a recompiler for the CPU code in, because I think the CPU right now, the way I have it planned right now, the CPU is going to run at 150 megahertz. Although I've been thinking about it, so it's going to be running at 150 megahertz, and the GPU is as well, and the video output is going to be 640 by 480 at 60 hertz. I'm actually thinking to half the video resolution, because then you need a quarter as many pixels. So that'll be 320 by 240, again 60 FPS. And then I'm also thinking that, I'll probably still have the HDMI output 640 by 480 because that's more compatible, but I'll change the actual video buffers and resolution to be 320 by 240. And then I'm also thinking to double the CPU frequency because I think I can without much issues. So just seeing these numbers here, how much this went down and this didn't go up. I'm not convinced this helped us too much yet. Oops. Yeah, so it looks like the signals coming out of this are a bit simpler now, but overall still hasn't helped us too much in terms of trying to make this a block RAM. And I'm not entirely sure why that is. Yet. It did go down a tiny bit though. I'm just going to take what we have so far on my notes here. Actually, we have more registers and less logic elements. Same memory bits. I haven't thought about doing 16:9 because I thought 4:3 would be more error appropriate. Even though, you know, cranking up the clock wouldn't be, but yeah. The emulator would probably be pixel perfect, but it definitely wouldn't be cycle accurate. I wouldn't do it cycle accurate with this fast of a CPU. Hey, my sister. Yeah, the graph load's way faster. It's a lot simpler now. You know, there's actually a quick thing I wanted to try here. I wanted to see if removing this might help. Just removing the initializer. It probably wouldn't. G-Sibling, the biggest thing we did was we changed how the registers are read. We removed all the RD-1 things because we actually added register 0 as an actual register. And then we did some stuff about when it was actually reading from that register, so it was able to reduce a lot of the muxes. So it's just a couple of those somewhat fundamental changes that just kind of went through the entire setup, simplified a bunch of things. Lord Gravis says, not sure I understand what you mean by regarding splitting off blocks making sequentiality less obvious. I would expect the opposite by increasing readability and defining module responsibility more strictly. I was thinking it would be simpler because now we could just sort of look at the behavior at each state, even though the state that it operates on, that behavior, is a little bit mixed up. But it might be worth doing that anyway, just because it might end up being a lot simpler anyway. Okay, this was interesting, actually. This, I think we might have gotten it by doing that. Hold up here. Yeah, I think we got a block RAM, you guys. There it is. We got a block RAM. Sweet. So what I just did there, if you didn't catch it, because I didn't think I said anything about it, is I just removed the initialization. So instead of them being initialized to 0, I just removed that, because that way it removed this reset logic. So it's always going to write that synchronously. And then, oh, I love when I'm starting to understand this now. So now we're down to about half the logic elements. So 1727. Total registers went down by a third. We have 508 of those. And our membits went up a bit, which we totally expect. By like 3,000. Which 32 by 32, of course, is 1024. But if there's some extra stuff on like the read and the write ports, that actually could totally add up to what we see here in the increased memory bits. So that's awesome. But yeah, after trying to simplify this logic, I am starting to see the appeal of splitting up the different stages more. So I'll have to think about that. Admittedly, Daniel Collin, it's still a bit magic to me too, but I feel the intuition growing at least, which is the goal. Pyro, yeah, I was at something. At least the beginning of Thursday's stream, I was at least over 6,000. somewhere around 6,000 or 7,000. Now we're down to 1,500, just with some simple code changes. And the only thing that's really more complicated now is that I've been using this 2-process style, and I kind of have to break it a little bit in terms of having these combinational signals that don't follow this next convention be part of this. But I think that this is well worth that effort. So I think the red flag that should have gone off in my head initially was just how that netlist exploded, because I don't think it should have with how simple of a design this could have been. And like I said, it was Per Vonsen that really pointed a lot of this out. So again, thanks to him for leading me in the right direction, giving me these specific tips. There is still more we can do here. Like right now, the misaligned reads and writes or the unaligned reads and writes are still a bit more complicated than they have to be. I definitely want to fix that, and that will also probably involve splitting out the instruction fetch units and some other things. So yeah, there is some more splitting I want to do anyway. Right now, I'm thinking actually too that we can split up the register file into its own module, because that would be nice. Yeah, this would actually be super natural to split out like this. These RS1 values as well. I mean, they'll just be the different outputs, and then these RS1 are the different addresses for that. I'm actually going to do that just because I think that'll make this read a lot better. And I'll still have to think in my head about splitting this up into separate stages, because I'm starting to like that, warm up to that idea for sure. But I don't know if that's what I want to sit down and do today, because I'm hoping to get this a little more simplified and start working on the other units, but we'll see. We will see. So yeah, I'm just going to call this register file.sv. And this should be basically exporting the exact same interface that a synchronous RAM would. So module register file. Hey, let's get this. Yeah, I think you're right, Lord Greybush. And as I'm seeing this and seeing some of the changes we have to make to make the logic actually simpler, it's starting to make more sense to me to start splitting up like that. I was definitely thinking the state machine approach would be the simplest. And in the end, if I split all these up, I'll still have that state machine that just enables the different units or not. But yeah. Although they probably don't have to do that either, really, because I can probably just run them all and just have different pipeline bubbles, but we'll see. The values are probably going to have junk on startup now, which is fine, because I kind of expect that. It should be possible to make an explicit blockgram and specify that the initial values are all going to be 0, but that's not what I want to do here. Another thing that I've been thinking about doing is removing these asynchronous resets, which I'll probably do pretty quick here. Whoops. That's a good point, Daniel Collin, is that register 0 might not be 0 now. That would be bad. That's something we'll want to fix. I'll split it up into the register file first, and then we'll look into fixing that. That's a good point. So I'll have write enable, and we'll do an input 4 down to 0. Write index. We'll call it address because that probably fits better naming wise. Then we'll do our 2 read ports. And we can just use the same read enable for both ports. That's like we're doing already. That's fine. These also need to be, oh, those are inputs. So as far as I know, this is just going to be like all the RAM is going to be on the sync RAM that we're using for the register file is all going to be just reset to random values just because of the random state of the of the transistors inside the RAM. And then the microcontroller would normally set those registers, except it can't set R0 because we can't write to that. So that's the one that we need to either reset to 0 or, as Lord Gravish points out, index from 1 to 32 and hardcode index 0 to return 0, which we could also look into doing here. So we need read and enable. We need read adder 1. But Vonson won't it not be initialized? Because I haven't specified anything for it to be initialized with. I mean, I haven't added back the signal tap, so I don't know what's actually in here, but yeah. Yeah, I'm keeping the PC as a separate thing from this. Oops. Fix that. These are also going to be clocked here. I mean, really, let's do it this way. Probably just do it like this. That's the only one we really care about anyway. What? Come on, why can't I type today? So it should be fine not to set, of course, values for all this stuff while this stuff isn't set, because these are registered. So shouldn't have any latch issues here. Whoops. That's wrong. We want this like this, and then input 31 down to 0 for the right data. And I'll do that after the address because I think that looks nicer. And this, of course, needs to be non-blocking assignment. Yeah. Nice. So I think we can basically just rewrite a couple of these. Just do this. Can clean this up later. Oh, I hate when it aligns stuff like that. Hate it, hate it, hate it. I'd rather type it back out. Fix this stupid alignment crap. I hate that. Do this here. Come on. Probably just configure the editor plugin to not do that at some point. We need the addresses that are mapped here as well. All right, I'm going to configure this. Seeing how to disable it. Man, this stuff annoys me. Configuring editor plugins sucks. I don't give a shit which editor you use. Well, I think I might just be able to just disable all completion because it's not really helping me anyway. That's actually cool. I can use initial to initialize the contents there. Especially since I really only need register 0 initialized. Sorry, I'm frustrated by trying to figure out how to configure this stupid editor. I think, though, I just set this thing here. Let's see if that helps. Yeah, we'll go with it. Anyway. Okay. Nope, that didn't help me. Oh, I'm so annoyed with this. But I'll just deal with it for now. Fix it later. This will actually just be RD when I think about it. And the adder here, yeah, this is actually going to be RS1. And then something like that. And then these don't need to be set here, I think. Because the read data here is going to be flopped from the register file. And of course, we don't need any of this now. I think we're good with that. We'll have to see. Couple things we need to add. Oops. We need to add this into our make file here. Put it here. And That should allow us to test it here. Looks like our lead values have totally changed values. That doesn't look promising. Should have register file here. I'll append all these. Yeah. So register 0 is totally writing values to that, and I'm pretty sure it's because of this. That's probably why. Yeah, now they match. And reg 0 should stay 0. Cool. That makes sense. And we'll compile it here just to make sure that we get what we expect. Although, not yet, because I need to add the file here. Also, sorry about the link there, Pear. I'm going to add you to my whitelist. Done. Okay. Just judging by these numbers, I'm guessing it did not infer the block RAM this time. Probably because I initialized that register 0 value. So we'll have to change that. Or maybe it did, actually. It would make sense, actually, that would happen after place and route. So actually, it looks like it did. Whoops, I did not mean to do that again. Ah, whatever. Meant to open up the programmer and click the wrong thing. This just reminds me of sitting here waiting for the Virtual Boy to flash. Yeah, that looks fucked up. So read buffer here. Oh, this is actually a register file. So I think the layout just got really weird and that our logic actually didn't really get much more complicated because what I'm seeing here is what we expect. This looks great for the register file, by the way. This is awesome. Yeah, so actually, check this out. This inferred a clear 0 thing here, which it uses on reset here. That looks great. Although, do we need these registers here? Of course, I'm pretty sure it added this clear 0 because I wrote this. But whatever works. Yeah, I'm gonna just do that here. Well, I think it inferred registers because I had logic here. Let's see if I just remove this. I want to see what that compiles to. Make sure it works the same here too. This to me raises the latch red flags in my head because from what I understand, I'll set this up to compile. From what I understand, this exact case where you only set the outputs on some of these conditions would cause the compiler to infer latches for these values. So I'm not entirely sure if this was the right way to do this, but we'll see what the compiler gives us. If nothing else, we should be able to see the latch there, so. This still looks super messed up in the layout, but we have fewer logic elements here. So I'm guessing it's still an improvement, and simplifying some other logic will probably just fix a lot of that. Yeah, so this is still seems to be doing registers here, which is somewhat interesting. I mean, it may be that that's still correct. It just seems a little odd to me. It's cool, though. It has the two read ports like we would have expected. Data out and port B, data out, I guess, what looks like these are. Like, these are still clocked registers. And the muxes on the inputs of these look exactly like we would expect. So, it's not like it's doing the wrong thing, I think. But it's weird because I would have expected those to be latches, not clocked registers. So I wonder if it's inferring that these need to be registers based on that sync RAM. What I'm worried about here, but it's not clear to me based on the data I'm seeing. I'm reading your comments, Lord Gravis, by the way. I appreciate the help, but it's it's not all adding up to me, to be honest, because regardless of whether or not I'm writing like logic here, it seems to infer these as registers. And I'm wondering if the sync RAM just needs to write those registers explicitly. I wouldn't have expected that to be the case because I'm pretty sure it's clocked, but the fact that generated like clocked registers and not just a latch is really concerning to me. Let me see if it gave me any warnings here. Of course, I got a lot of incomplete case statement. I don't give a shit about that right now. I mean, maybe I'm just confused because I just wouldn't have expected that to infer clocked registers. I would expect it to infer a latch. And I'm assuming that latches aren't clocked when I say latch in this context. Maybe that's the thing that I'm assuming wrong here. So if this stuff annoys the crap out of me. So if I set this to, for example, I really don't want this to be X's, but I'm just gonna try this just to see what the simulator gives me. Man, I'm annoyed today, you guys. Something like that, I would expect to not infer the latches. And I don't know what this would give me in that case. But I want to see what this compiles to. Of course, it didn't work here now. Ugh. Let's check the netlist here. So I understand that wires need to be driven. I totally get that. I just what's bugging me is that it was clocked because my understanding was that it would do an unclocked latch, which is why you want to avoid those. Just go in here. Yeah, so now we've still got the registers here. It's just there's no muxes feeding back, which I guess is better because we don't really need those values to feed back. Assuming that this is still going to hold its state as long as the data in and everything is valid. Because that's what I was thinking is that if this had registered outputs, considering it's a sync RAM, then we would be fine. But now I'm wondering if it's trying to infer these just to make sure those are registered. It's just a bit weird. The consequence is that we would get a cycle delay. On the cycle that we would expect to get the outputs of here, so we would clock out, write and read we would clock out like the read enable signals, and then on the next cycle we would expect these port values to have the data that we need on them. So having an extra register here just seems like that would introduce another cycle delay, because they would be clocked out here first on the inputs of this, and then they would take another clock before they would reach the output of these registers. So it just seems a bit weird. And considering the CPU seems to no longer work in the in my simulator here, that's a bit concerning. It does seem a little strange. Although I am not seeing a clock here. Well, yeah, I am. The clock goes here. It does seem a little odd. Because if it weren't clocked, then the logic that we had before would have been what we were after here. I also got way more logic elements here, which is also concerning me for a different reason, but I want to figure that out. Oh, wait, let's do this. Let's remove the fact that I wrote logic here, which I don't think I would need, and just keep it how it was here. See if that helps. I don't think it will. Yeah, still not working in the simulator. It's also weird that I didn't get any warnings about this. And it's weird that my number of logic elements went back up after I separated this register file out, but we'll have to see what's up with that. We'll just have to see. It's annoying that these like go down after place in route, but I'm not that surprised. I think that's actually when it infers that it's going to use the block RAM anyway, which should make sense because it's at that point it's kind of matching the net list to the underlying hardware, I would imagine. It might know that it can during analysis and synthesis, but who knows? This still got so weird. I'm guessing though that'll be easier to simplify. There's probably just hooking it up wrong. But here, yeah, so without that logic, this is still the same. It does seem just so weird that this is, I'm guessing, a cycle late. So I can't imagine. Like, the thing here is that this code here, this netlist viewer we're seeing here should be exactly this logic and nothing else. This on its own, this is pretty weird. I at least think the inputs to this makes a lot of sense. Because this logic here is very simple. This is we have the right adder here, and if the right adder is not equal to 0, and right enable is true, then we're gonna have right enable here. So that looks great. Whoops. Don't know what I did there. There we go. But it really seems like the output here should already be registered. And I can't imagine the usage of this module would change this. It also clearly knows that this reset is, well, right now it just uses it as a clear 0 signal, which is fine. It's active low, so this not here is correct too. Yeah, I might as well try that. But yeah, it should definitely know that, just the way that I'm assigning here. It's annoying that I have to start being explicit about that when I started using logic so that I wouldn't have to be. Also, it really bugs me too that it's just not working at all in the very later simulator. Which, although I'm wondering if that's higher level issues with how we're using the register file, because I don't think I've changed much there at the moment. Oh, this is annoying. Yeah, I guess optimizations could affect that. Yeah, so we're still getting these registers out here. That's just so weird to me. We could look at how this is actually used, though, just to see if that helps. I'm gonna remove these wires here because they didn't help me here. Okay. So how do we drive this thing? Here's our register file here. And we have these read and write enable things here. And these RS read enable and RS write enable. Write enable should be here. It always sets the value there. There should also be another write enable at the top of this. I'm just going to set to 0. So by default, these aren't going to be used. And these are all just combinational signals, which should be fine. Hit our second. And actually wanted to look at the read one. Yeah, read one is either 0 unless we get the instruction decode state, in which case our instruction data is already valid, so we just need to do the read enable. And we have RS1 and RS2 here are our addresses, and that should make sense. So we'll get read enable is high while these have the right value in them. And then we're going to pull out those values into these. Really, these should be wires, but yeah. RS1 and RS2, they come from here, which are assigned from these bits of the instruction register. So I think that should be okay. They're combinational signals, but I can't imagine that being a problem. Because the read enable is still going to be synchronous here. Or, well, that's also combinational, but still. That stuff really should be fine. As far as I can tell, this stuff looks good. And then the actual value of these... I guess, though, these guys, the values here, these are going to be combinational. So it might need these registers on the output of this, but it's so weird because I would imagine this the memory itself would have been registered like that. Would have had registered outputs on its read ports. That just seems so weird. Start digging through docs now. Hey, Oncodes. Yeah, I've been streaming on Saturdays lately. Doing some hardware stuff. Man, I was really hoping this would be this would be a really straightforward day. This really does seem strange. Problem is, there's a lot of this stuff to read through. I may do this later. I don't think this read during write stuff should be a problem either. It never, I mean, the synthesizer has no way of knowing that I'm not doing that. But it should be fine. Regardless of what data we get out, as long as it does something, this actually should be fine because we're not doing it at the same time. You know, another thing that I could do though. I could just take in like a sync RAM sort of interface here and just bootstrap that at the top level of my project, my hardware top here. I could just instantiate a specific block RAM that I create through the Altera software and just have the CPU require that interface be patched down to here. And I guess that would be okay. It just really bugs me that this I just don't really know why this doesn't work how I would have expected. Because the other thing that's weird too, still, is that my logic elements and my registers, exploded again after I split this out, and I didn't really change the usage at all, from what I can tell. A lot of crap in the QSF file that I just don't care about. Yeah, so and we did have that other state, but that shouldn't matter either, because that actually helped us before we did that. Wait a minute. I only seem to remove the right stuff. Did I? Oh, that might have also been because I think I did this in 2 steps. I didn't commit between them. I did that in one where we changed the register reading to also happen synchronously, which got us our block RAM at first. And then I didn't commit, and then I started separating this out into this other file. Here's what I'm actually going to do right now. I'm actually going to delete this register file thing, and we're going to go back to where it was between these 2 stages, just to give me a better point of reference here. I'll just do some of this again. So we'll discard this. I mean, I can't imagine why we don't need to discard all this stuff as well. Well, I'll just discard all this. Except the state stuff, as we did want to have that other state in order to make this work. Yeah, because we wanted... Oh, I'm so bad at typing today. It's so annoying. That should be set to 1. Did I not? Did I trash that part? It's not my intention, but that's fine. Oh, so bad typing today. Okay, do this, and then RS read enable, set to 1. I at least want to just commit this here so I can better keep track of what I changed after this. That's really what I'm trying to do here. Oh, I think I know what I did wrong here. I think I just did my checkout options backwards. I hate when I do that. Yeah, because we actually did want to remove... Yeah, this is what we wanted here. if rs read enable I think that's what I had. Guessing rs1 value is up here again. Okay, so now it works again. I think I see what you mean, Lord Gravewish. It does seem weird, though. Could definitely try doing it that way again. First, I'm going to compile this. This should match what we had before we tried splitting out the register file. I still want to try doing that. I just want to do it from a... I want to get a better last known good configuration first. I mean, on one hand, it's kind of good that I'm fighting with this stuff because I need to learn how to. On the other hand, it's annoying that it's a problem. Okay, I actually got some interesting warnings here. Oh, hey, this is actually cool. Inferred RAM node for some of this stuff. That's cool. That it told us that. Weird stuff here, though, but we'll get to that. Yeah, our logic elements and registers kind of exploded here again. Ugh. Yes, we did get our value here. Oops. And we also got value 1 and 2 here. Also, kind of weird that it got the correct values for some of this stuff. So here we also see in this configuration that we do have the synchronous RAM here. And then the same muxes that we saw before with RS1 value and RS2 value. Including feeding back in here, it looks like. I guess that's to be expected. Weird that these got so high again, though. Although I might know why that is. Yeah, because we have signal tap in here again. That probably explains that. Because when I did the git checkout again, I probably overwrote that file. I think that's what we just saw. That it was still inferring the registers after the muxes. Yeah, these numbers look better. Yeah, so now 1720. Yeah, so we're looking a lot better in terms of these numbers, which makes sense. That's just without having signal tab. Yeah, I'm pretty sure, because these are the registers here. There's RS1 value and RS2 value here. These are definitely registered after these muxes. This to me looks like exactly the same configuration that we saw there. The registers here, and then the muxes, and then the values. Although it is kind of interesting. Yeah, the output of these only comes from the output of the registers. That is the goal, Dark Second. Seems like we're having a bit of trouble getting much further than this, but that's okay. I'm also guessing a lot of the logic out here too is again the misaligned writes and reads. We'll get to that. I think this is our ALU down here. That's our read buffer. That probably makes sense. I'm going to commit this right now, though. I guess this is all the signal tap stuff. That's probably where that came from, which is fine. Yeah, it's probably one of those two, Greybush. The big yellow block in there, that's the state variable. Dana Colin, I've actually already implemented them in hardware, and I'm not happy with the implementation. I'm going to keep it in hardware because then I don't have to figure out how traps work yet, which is kind of what you need for doing those otherwise. But I'm definitely going to simplify that. In fact, I might do that now and try to come back to this register file thing. Do BRAM for register file. Yeah, there's no clear here. And we don't know what the default value for the sync rem is going to be, so it is totally possible that R0 is incorrect right now. But yeah. That's not it, Freefall, because we have to support unaligned loads and stores somehow. If we ignore the lowest bits of the pointer, then the issue is that we only have support then for aligned loads and stores, and that's not correct. What a simple implementation can do in hardware is just ignore those and only have, aligned loads and stores. But then they can trigger, if those bits are not 0, they can trigger a trap or like an interrupt, and then that will the software can then do the individual reads and writes that are aligned to make the equivalent unaligned read or write. The RAM in the CPU, this is the register file. We're trying to get the in order to simplify the design, we're trying to get the synthesizer to infer that our register file should actually just be a block RAM, because that way it can use like the sorry, jumping between contexts a lot here, guys, but the FPGA that I have has a bunch of block RAM units on it, and we would rather use one of those than a huge network of logic elements and muxes, because then we're going to utilize a lot less of the built-in FPGA fabric. So in order to do that, we want it to know that our register files is really just some synchronous RAM. So that's what it is. It can freefall, but if we use a C compiler, the C compiler might generate code that does unaligned reads and writes. And then that C code would be incorrect if we didn't support that somehow in the underlying execution environment. Right now I'm doing that in hardware. That could also be done with traps. But because I don't want to figure out how traps work, I'm going to keep it in hardware, but I'm going to simplify the design that I have. That's what's going on there. Now, I still think it's weird, though. I guess I can understand this rs1 value and rs2 value here. Let me see here. rs1 value here. I'm going to actually try something here. Can I just do X like this? We'll see. I'll just do this. And also this is wrong because this needs to be 32. I want to see if this gets rid of the registers there. Yeah, or Rust. I haven't bothered to try building that toolchain yet. I guess the latest GCC actually got proper support for risc-v built in, but the GCC that shipped with MinGW in MSys is not up to date. And the Mac story is a whole other thing too. This actually seemed to go down quite a bit here. Just by doing that, which is somewhat interesting. Let's see if this still made sense here. Yeah, so that seems to be what breaks it. Seems like I had some logic in here that expected those to be registered. It's interesting that it breaks in both the simulator, breaks in the simulator and reduces our logic count here. I just want to look at what this is doing here. So this is definitely simpler, and if we look at here, I think, yeah, our registers went down from 508 to 356. And we dropped by another 120 logic elements or something. And looking at this, it's interesting that we still get these registers. I'm guessing a lot of the other interconnect goes away just because the output value here could be whatever, but it is just really interesting that it still keeps the value like this. But it got rid of the feedback in the muxes there, it seems. I just find that so strange. Are you sure about that, Gravewish? Because I think the state machine is all combinational stuff. In fact, I don't think I said it anywhere in there. Like this, all the state machine stuff is completely combinational. I read from it there, but I never set them there. And so the only actual transitions are here. And so I have them here and in both arms here. So I'm pretty sure I still am doing that. Man, this went way down. But it doesn't work, so it's not helpful yet. Here's one thing I wonder though. So we get this combinational signal, and then on the next transition of the clock, the output here will be set to this. And I'm assuming it's going to stay there for that entire cycle while this is still, before this has a chance to be deasserted. So these should be valid. Actually, I think it's here. Those are only going to be valid here. Yet here we also read from those values, and these are just going to end up being x's. Because the value here, we're not reading right away after this. So we might want to pull those into different registers as well or something for the stores here. Freeville, I think we can't make that assumption. It's likely that the compiler won't generate those, but it is in the spec that unaligned loads and stores on risc-v are allowed. So I assume the compiler would be able to take advantage of that, and it would be really easy to make like it shouldn't be undefined behavior on this architecture. It would be really easy to make code that would do that. Yeah, I probably actually could do that. Probably could do the read logic assignments in a separate block here. I might try that because, I mean, now we have this last known good state right before this change anyway. But I'm actually thinking, too, that I definitely read these values. I think this is why it doesn't work. It's because I read RS2's value here in this store state. I think I want to try and fix that first. I'm guessing if in this execute stage, if I just pull that into a register, which shouldn't be that bad having that other register here, that might just fix it. I'm thinking this. If I do Sure, Skidmore, thanks for the sub. Appreciate that. I definitely need the good luck today, I think. Yeah, you might be right, Lord Gravewish, that it might just assume those are registered because I'm only assigning to them within that kind of block. So let me try something here. So I'm just going to this down here. I'm gonna just stuff this up here. Because why not? Crap, where was this? Here. I'm going to use the store address. We're going to put that into a different register. I'm going to do a couple things down here now. And then instead of all of our stores here using rs2 value, these can now use store adder. That probably at least fixes the behavior. Seems to in that simple case. So that was probably the issue there at least. Not having latches where we think they shouldn't be is another thing though. Or not having these registers. Ugh. So I know I use the register output one cycle. Do I though? Because I use it on the cycle after. So I set my next value to be 1 for the read thing, but that doesn't get clocked until the next cycle, and then the read line should be high. And during that cycle, that's when I read out the value. In this case, with the stores, I was reading it back also a little bit later, which I guess was part of the issue there. Whoops, I keep hitting that stupid compile button when I want to open the programmer. Yeah, right. So it's after I use it there. So I think I was okay in terms of reading it. When I was reading it here in this stage, that should have been okay, because then this value gets latched on the next cycle. So then these ones should be okay, but then the fact that I was reading this after is if I understand you correctly, and if I understand this correctly, because I was also reading it like down here, that must have been why it was inferring the register. Let's see here. Whoops. I'm seeing no register here. Unless that's these. Which it is. That's annoying. So now I'm not sure if I am understanding you correctly. And this is frustrating me because... I'll explain why in a sec. Where did that store address get used? The store address should be registered. And I was assuming that that would come off of this too. Might be back here, considering where it's going to be used. Trying to see if I can, like the right address here. Only going to come from a couple places. I wonder if I can search in here. Find. Didn't like that. I called it store adder, didn't I? Here's the store adder. This I expect to be registered. Where was this, by the way? Okay, it's kind of far away it ended up being, but... Just looking at the inputs to store adder, which we'll get from D here. That came from over here, and it's this bottom one. And then that was down here. And back up here. Here it came out. Maybe tied to the Q of RS2 value. That's a bit weird, isn't it? Although that might be something else. No, that's definitely where it's pulling that off of. I mean, I guess that makes sense because if this were... Oh, this is just weird. Is that really the issue? I would have assumed that this would still hold its value, but I guess that's true. The only way it could hold its value for like this is if it were the output of a register. The thing that's frustrating about that is that assigning this to the output ports of the RAM, if I did that in, for example, a continuous block, then that would mean I'm reading this continuously. That I don't like, unless I somehow register the addresses. It's just a bit odd. So I was planning on streaming for about 2 hours today, and it's been 2 hours. So this has been annoying, to say the least. That's how it goes sometimes. I'll continue for a little bit, but I might give up on splitting out this register file right now. Or a pretty quick here, that is. Figure it out later. So the addresses aren't registered specifically. They come from the output of another register, so they technically would be, but they are from some combinational logic off of that register. Yeah. Ferris always debug stuff. I'll definitely figure it out in the shower. That's how it definitely works. All right. I'm going to take a minute here to think. So here's what really bugs me about this. For example, when I set read enable, this is going to happen sometime before the clock event, right? Let me paint this up. So we have our event here, our clock edge. And at some point before this, I'm going to set read enable to high. So it's definitely high at this point. RS1 and RS2 are also going to be, they're going to have their values also set within this period before this clock happens. They're not actually registered. Well, they are, but from a different register. They're not registered themselves, but there's a, it should basically happen here before the clock event before that. Or that's not where I meant to do that, to draw that. I meant to draw that here. No. Hold up. Yeah, I think I know what I want to draw here, actually. So I have a clock edge here. I have a couple events. On this first one, I'm going to end up setting my address, and then it's going to have its value here. So this is the instruction. And then RS1 and RS2 are going to get their values at that same time. Or rather, so yeah, sometime later we're going to get the RS1 and RS2. And that's these here. And once we have that instruction, read enable is going to be high on that next clock. So I guess what happened here. So we need a third one down here. And this is where that read would actually happen. So we have our instruction, we have our addresses, and we have our read enable. And the value ends up being read here. And then those outputs are going to be assigned at this clock event here. And if the BRAMs are non-registered, the only way that this could hold its value is if that was registered. But if the BRAM were registered itself, then this assignment should still keep its same value throughout the clock cycle until the next one, is how I understand it. Because the only other way I can write this, if I actually want these values to persist, like, it's weird because the way that this is written with regs as registers, I would expect these values to also still be the same whenever you do this. Maybe it's the fact that these aren't registered. It's just so weird. Let's signal tap this bitch. Whoops. This is infuriating. So I got a bunch of signals in here, but there's only a couple we're going to want to watch here. I'll do my pre-synthesis as well. Probably have to recompile with this enabled now in order for it to find these signals. I am actually going to recompile this really quick just to see if it can fill in more of those signals. Maybe it won't help, but it'll make me feel better. It's annoying because this was working before we tried to make it simpler. I guess that's how it goes. And now these numbers explode a bit because we're adding all this analyzer stuff to the design. Okay. Now we see if this helps at all. Probably not, but we'll see. No, I did not want post fitting. I want pre-synth. I hope it's so we have these R and these C's. Where is my read enable here? That's bugging the crap out of me. That I'm not seeing it here. RS read enable. No matches. Why? Why the hell? Are there no matches for that? Okay, well at least we can output the states. And we can look at RS1 value and RS2 value. That should hopefully work. Oh boy. Hey, 2D6 Tech. You didn't miss much. Just a lot of fighting with the hardware. Or rather the compiler. And mostly my brain. The struggle has been real today. Let's just put it that way. Okay. All right. So couple things I want to just look at here first. It seems like it's working. But there were a couple things we wanted to look at. We wanted to look at these RS1 value and RS2 value here. So we get to this decode stage into the execute stage. So the decode stage here. Also, really quick here, I'm going to just check our RTL here. Why does it need to save changes for a signal tap? Yeah, so here again is our block RAM that we have for the registers now. Fantastic, but we have RS1 and RS2 value here. So here's what's kind of interesting to me. On instruction decode, we set RS read enable. Which would have been, let's see. So we're in the decode state. And we set that to high. So that on the next transition, as we go into execute, the values here are read in. This to me tells me that this sync RAM is not registered. And maybe the reason why we're getting all these registers at the end of this is because the addresses aren't registered. And this would be the only way that could work. And then due to the fact that I'm expecting those values to stick around, it must be inferring registers. So instead of having those registers inside the block RAM, it's putting them on my signals. I suppose that clarifies some things. The fact that it works is also nice, again. Not every time, Freefall. I have to explicitly download it to the FPGA, but it doesn't take very long. I'm actually not doing that most of the time. But just now when I opened up Signal Tap, I clicked a button on the top right that downloaded onto the FPGA right before I captured all the data. Most of the time I'm not, though. I'm just compiling everything. When it's flashing to the FPGA, it usually doesn't take very long for like a normal cycle. It takes like 30 seconds if I want to update the FPGA's internal configuration RAM, but I usually don't do that. I usually just upload the new design. And then it doesn't persist. So if I turn off the FPGA, it's not still going to be in there. So I think, I imagine that's what would happen, Lord Gravewish, but I guess I would have to register the inputs, which right now are combinational. I mean, I guess those would still be the same, but I think the issue that we had earlier is that if I didn't do the assignment in there, if I didn't assign it synchronously, it couldn't actually infer the block RAM. And I think that was because Altera didn't have unregistered block RAMs. I think that's what it was. I think that was the issue that we had initially. This is why I wanted to do this synchronously anyway. Which is also weird, though, because it is, if these are unregistered, this shouldn't be an issue. So then this would stay the same, because we only want to do the write on the, when that's valid. So the way we would do this here is, again, we'd just pull this out. So we can try that. And I'm guessing what happens is the block RAM goes away. So if I remove that and we go back up here and we just do these assignments here. Which I'm guessing this is the same as just putting it in a combinational block. I can't imagine this would be any different. I guess because it would tap there all the time, but still. I don't think this would really be any different. And again, this should still work in our simulator. And it seems to. And so now the first thing, actually our logic element count looks pretty good here. Compared to what it was before anyway. Yeah, at least the read input stuff should be registered. I think. Oops. Okay, so we still got our block RAM here. That's nice. Huh. Maybe this actually just fixed the problem. What is my registers did go down again, 46. Logic elements went up a tiny bit. I'm not too concerned about that. This is the current design on the FPGA or versus the FPGA. Data Colin, I have about 50,000 logic elements. I'm only using about 3% of that. Is to answer that question. So here, I kind of want to see there. Yeah. So here's that instruction register. Here's our store adder, which we do expect to be registered and happen a clock cycle later. So the fact that we see this routed, this should come from the output of this eventually. Yeah, we're definitely not seeing the registers now. That's nice. You know, I think I know why this kind of worked out the way it did, though. And I think that's because, so let's see here. Right now, first of all, this read enable thing doesn't matter. We're not using this now. So I'm actually gonna remove that. So then we just have this useless state in here. I'm a little weirded out by this, actually. But you know, I think it might have been because now I'm using this store address. So I'm only actually reading the outputs of this on the next cycle. there's some weird stuff going on still here, I think, because this doesn't really line up. This, you're thinking about single tap, Mr. Anderson, but that was not the case. We totally removed this by replacing the stuff with block RAM. That's where most of that went. I did also disable that, which is why. Yeah, okay. So actually, never mind. Sorry, I'm so bad at jumping around between contexts today, you guys. Yes, most of the logic element count, that was absolutely a lot of that was signal tap. So I did disable that. But when I disabled that, it went down from around 6,000 to around 3,000. So that was a signal tap. And then being able to replace our register file with a block RAM, that got us down from around 3,000 to around 1,700. So those are sort of the two major steps. But I'm kind of concerned still here at what actually allowed us to infer the block RAM, because right now we're not even using that enable signal. And in fact, if I look in here, back at our RTL viewer, here. Yeah, so there is no like read enable here. Or it's just tied to 1 is what that means. It's just probably what that is. I just think this is so weird because, let me see. The writes are still synchronous. The reads are not, and I think, let me see here. Why I'm concerned a little bit here. First of all, I just removed that RS read enable. I'm not confused that the read enable was fine. I'm just going to compile this to be damn sure right now. What I'm concerned about is that I had this same pattern before. I made the writes synchronous, and the reads were still asynchronous, or rather combinational. Yet I didn't get a block RAM. To try and get the block RAM, I also made the reads synchronous. And then we got the block RAM, but we also got registers on the output of it. What I think the actual change was, and I'll test this, but I think it was actually just that here, on this execute stage, I only read in RS value here on this cycle after that. It'd be weird if it knew that. But I only read it on the cycle after. Again, that shouldn't matter. I'm really confused at which particular change I made actually did this. Because I totally had synchronous writes and combinational reads, and it didn't infer a block RAM. And now somehow it's doing that. And I'm not happy about that. That's why I'm not convinced here. I mean, what the design that we have here is what we wanted, first of all. So that is nice. But I just am not I'm not convinced about which change we made was actually the one that really made the difference here. Crap, I do not want to. I don't want to git diff the signal tap stuff, so I'll just check that out again. I had R0 split off before, but I fixed that when I did the writes. When I did the synchronous writes. You know what, though? Yes, when I disabled signal tap. Because it was also during the same commit. During the same commit that I went to, I think it was this. Because during the same commit that I went from asynchronous reads to synchronous reads, I also removed this initializer. Let's do this. Let's add this back, this initializer, and see if that breaks it. That would have been this. So I'm thinking that that was actually the change here that did it. And then the RAM that we're getting here doesn't have synchronous registered outputs, which would be fine. I might just squash this with the last commit. Nobody's looking at this on GitHub, at least, or no one's cloning this and working with this, so I don't mind force pushing to master as long as I can get the right information there. I'm still a bit concerned though about register 0 being wrong, but we'll see. Because I need to make sure that register 0 is actually going to be 0. Things are still a bit fuzzy in my head, but it would make sense if this were the change that did it. So now I'm glad I committed between those two changes just so I could see both side by side. R0's value needs to be 0. That's part of the spec, the hardware spec. Or the architecture spec. And a lot of instructions use that. A lot of instructions. So our LEs are a lot bigger now. And I'm guessing, yeah, now we have regs and muxes again. So maybe it does have a clear signal, and this is just not the way to do that. It's just not the way to make sure that gets cleared. So it seems like that was the change, which is, I guess, good to know. Let's try doing this. Just want to see if clearing that first one works. I think that worked earlier, but I'm not sure. I mean, worst case scenario, I could totally have a startup state that just writes 0 to R0. I don't really care about that. Yeah, this is risc-v freefall. That way we get to have a C compiler without porting something. That's also why we need to make sure that we support the unaligned loads and stores, because the C compiler is going to be expecting that those are supported by the execution environment. And so here we're ballooning again. Although, interestingly enough, we do still get a register file as a sync RAM. And our clear 0 comes from somewhere that's probably reset. I'm seeing it's at least hooked up to a bunch of other clear signals. Mr. Anderson, that makes the compiler shut up. If I just put 0 here, the thing is that this is a 32-bit value. It works here because these are like 1-bit values. But if I don't specify the number of bits here, the compiler yells at me a lot. Maybe it doesn't in the case where you need a bigger value, but yeah, I've had issues with that, so I always just try to specify it. So there is a Rust toolchain to risc-v, but it's not an official one, and I haven't bothered to try building it because it looks somewhat complicated. Cert, if I'm reading that correctly, thanks for the follow. Well, thanks for the follow either way, but. So what's weird here is it's got so much bigger just to support that reset. That seems dumb. I wonder too, if I just do this. It's amazing how that drops this so much. I want to see if that clear signal is hooked up to anything now. But yeah, again, it wouldn't really bum me out that much if I just had an initial state that set R0 to 0. And there could be we'll see if that still makes sense. I want to separate this out into a separate register file now that we sort of know why those registers were there and what we need to do to make sure that we infer the block RAM. And then sit there and start playing with what we can do about R0. I mean, this looks how more or less how we want it. Daniel Collin, the specs do say that, and in fact, there are a lot of instructions like no op that actually do that. And the write is ignored. You're allowed to do that. So you have to support writing to R0, but it doesn't have to do anything. So it may be what I had before is that I had a bunch of compares on all that stuff, and I guess one of the reasons why I have a register 0 explicitly in the register file is because it makes the indexing, like for the read port of that, not have to do a -1. It might not have to anyway, now that when we start moving things around, but that is why I initially just had that in there. Although I am still worried about its initial value. And that's what I was going to look at. I was going to look at its clear input, which is probably disconnected here, or driven to 0. Yeah, it's just 0 now. Yeah, I guess that's why we're getting a bunch of this crap when I try to clear it. All right. So let's separate this into a register file now. This should be really straightforward now. I mean, really, it's that, though. We'll worry about reset later. It's definitely weird because that sync RAM that I'm seeing in the netlist definitely does have a clear input. It's just driven to 0 right now. That's weird that it says it doesn't support that. Because that's definitely seeing clear here. Or clear 1 at least. Maybe that's for port B or something. Who knows? I don't know, because here we have clear 1 and port B clear 1. Maybe it can only clear to 1 and not to 0. I don't know. Input right enable inputs. 4 down to 0. Right adder. Input 31 down to 0. Right data. And input read adder 1. Input 40 read adder 2. I'll actually chunk them like this, so you have 2 outputs. So then this should basically be read data 1 is going to be regs read adder 1. Read data 2 is regs read adder 2. Although I can just do this, I can just assign, which I think is a little nicer in this case if we just have this stuff and no other logic. Might be an issue knowing that this is registered, but I'm not too concerned about that at the moment. We'll see if it's an issue. Yeah, I do main clocked. Yeah, I'll do that. that for now. Something like that. And again, we got to add it to all of our stuff. That should cover this. And I broke it again. Ugh. Oops. Where's my instruction thing here? I can also do this, just to show these. Yeah, so our right doesn't seem to ever work. Yeah, I might know why this is, actually. Or, no, this should be fine. With what I was thinking, at least. Because these addresses aren't changing. Whenever we're reading these values. Let's run it through this compiler and just see what we're getting here. Which I can't do yet because I have to add the file to the project. Yeah, when you do like not equal to 0, it is just going to OR all the bits together. That's how that works. What? How? This went down a lot. Although we don't know if it actually works now. It doesn't seem to work in the simulator, at least. So those numbers aren't good enough until they work. But there's our read buffer. Here's our ALU, and here's our register file. Okay, so we're getting a write adder, or write adder. Ooh, write data. Ha, that could do it. That write data isn't hooked up. That's just this. If it's tied to ground, that just means it's all 0. That might also explain why the design got so much smaller. Oh, yeah, chief detector. Then you got it. Did I really not hook that up, though? That's what this was. Enable address and data. Oh, whoops. Right value. It's weird that it didn't give me any errors about that, but okay. Hey, Mr. Tome. Yeah, now it seems to work in the simulator again. Bloop. That's nice. That's nasty, Lord Greybush. That is not something I wanted to auto-declare. At least it was very obvious what happened in the netlist, though. No, I didn't disable that, Mr. Anderson. I guess that's why I should have. I took note of it and then forgot about it. But do I really have to put that on top of all my files? That's annoying. I mean, I guess it's better than the alternative. I'll do that right after checking this netlist. Yeah, so now we're looking stupid again. Which is the same thing that happened when we split this out last time. And I wonder if it's just because it's being routed dumb. Because we didn't actually add that many new logic elements. So it's probably fine. Oh, wait, that's a rebuffer. That's not what I was looking for. I want to find our register file. It's probably here. Yeah, this is it. So this is exactly what the register file should look like, first of all. That makes me happy, if nothing else. Phew. I'm happy we got to this eventually. If nothing else. Phew. And yeah, we're at a good number of logic elements and registers here. Basically, this didn't change now, which is also what we expected because we just sort of moved some things around. I'm going to add that crap, the default net type stuff now. That's super annoying. We're going to put this in all the RTL. Because screw that. Isn't that backtick? Isn't that what we're supposed to have? Even in all my DDR3 tests, I'm just going to put it on everything. Because we do not want this kind of thing to be inferred. So from what I could tell, it doesn't seem to infer that. I mean, it might do that, but the thing is, it's not going to matter the way we're using it right now. Really, what those semantics are at all, because we're not going to be doing that in the same cycle. I think I saw in the documentation that there are some different semantics on that based on if we could specify a parameter to it, or if depending on which kind of memory it used. But since we're not specifying, I'm guessing it'll just give us something. And then by not specifying, we say we don't care, which we really don't because we're not going to use it that way right now. Yeah, I think that's basically the same as what Lord Gravewish said. Again, in our case, it's not going to be an issue because we're just not we're not relying on that behavior at the moment. It may look like we are, but we're not. Not at a high level, at least. Well, if nothing else today, we did get the design smaller by finally getting this block RAM. And if doing that and sort of understanding why that happens is the only benefit we really get today, that's pretty good. Yeah, exactly, Mr. Anderson. Right now, even if I do pipelining, I think that would be better handled in the logic around it, like introducing stalls and stuff. I mean, I guess for a really efficient implementation, we could try to take advantage of that, but in that case, we would probably try to specify which kind of block RAM it was, or which kind of memory it was, to be more precise, or rather more abstract. I think. So this design looks crazy now. Like the layout still looks really weird, but we have reduced the amount of logic elements that we had, so it's a better design, even though it looks crazier. Again, that's not our register file. I'll just get it here. Hazards are just cases where in a pipeline CPU, you have contention on resources like that. Like that's actually a really good example. I believe that's called a structural hazard. TW Carter, thanks to follow. Or maybe it's data hazard. Don't remember, but it's a case where like if you have two instructions in a row, and then based on your pipelining model, if like one instruction we're supposed to write to a register like as a result, and then the next one were to read it, but because of the pipelining, it actually wouldn't work. That it would, like there might be some conflict between when that's the scheduling of those two events happened. That's a hazard. That's all that really is. And then the way you handle that, you can handle that in different ways. But I'm trying to avoid that at all costs in this implementation right now by just not doing pipelining. It's not a problem if you don't have pipelining because every instruction is effectively atomic. Whereas in a pipeline CPU, you've broken it down into the different stages. So then you have to ensure the correct behavior. Yeah, so it's a data hazard, not a structural hazard. I got that wrong. Yeah, like one way to do that is to stall other stages of the pipeline. So like stall the read stage so that everything else moves the data, and then allow the read stage to happen after. And there's many different cases there which is why I'm trying to avoid it. Maybe it's not as simple as I fear, or maybe it's not as complex as I fear, but yeah. One thing I'm actually wondering here is I added this store adder. I'm actually wondering if I need to do that now, because I can still just use this RS2 value, I think. I think we'll get the right behavior if I do that, and then we don't have to have the store store adder variable here. I mean, what I should do though. No, I'll just do this. Let's get all of them. I'm aware that I got some other ones down there, but that's fine because they'll be easy to pull out. We can remove that register. I don't think we need it. Yeah, so we still got our inferred RAM. It's actually, so forwarding actually does happen in a lot of these, a lot of RISC processors from the time period that I'm sort of working with here, like MIPS, V810. Those things actually all have forwarding. Forwarding is where you basically have a mux on the input to certain stages, and instead of reading it from the register file, it can actually just read it straight from the output of the other unit. So that's one common way to handle that. Which is, I mean, that stuff, like forwarding is still more complicated than I want this to be, but yeah. So I'm still a bit concerned, though, about the fact that we're not initializing this. I mean, I did just eliminate that other register, which is perhaps kind of nice. Although it didn't really help us. We did get rid of a bunch of registers, but we added a couple logic elements, but I would say it's fine. I do like having one less register in the design. Welcome back, Emma Sister. I'm hoping to do audio on the same chip as well. Doing the whole processing in a single cycle? I don't think that's possible, Lord Gravish. Because you have to do a fetch and then you have to have reads and writes. I'm not really sure what you meant by doing that in a single cycle. I mean, I could have the processing for all the different stages there, but... And that would be easier to pipeline. Maybe that's what you mean, but yeah. Hey, Dr. Bob. And sister, we've been improving, still making the design of our CPU a little smaller. Mostly by fighting with Cordis to infer a block RAM for a register file. The design looks crazier now, but it's smaller. So we kind of got what we wanted. Yeah, if I understand what you mean by single cycle processor load, Gravish, either each of the stages is a single cycle, which then I can do that and just have a state machine control which one is active, and that's easy enough. But in terms of doing everything in the single cycle, I actually don't see how that's possible. Thanks for the follow, Huggy. At least not for a risc-v implementation. The other thing I want to do here, by the way, I think I still have an extra state here that we don't need. I think we have a state here that just, I think right now it just goes to the next state. Yeah, it does. So let's actually rename this back to decode, which is what we had before. I guess I'll have to look into that, but I'm not seeing at all how that's even possible, at least not for a risc-v implementation. It's not making any sense to me how that would be done. I mean, I guess I get, because I'd imagine you'd have like a mode there anyway with stuff that you're waiting on. Maybe that's just what that means. So instead of just having a big state machine like this, I do different modes. But this, I don't know, this made sense to me. Yeah. Yeah, now we're a little faster again because that extra state basically did nothing. I just want to make sure that still infers the block RAM correctly, which of course it should because this was unrelated. But originally I set that up to register the inputs to the write, or register the inputs to the read. I guess since there's still wait states in a design like that, it just seems like it would be more complex to me. Yeah, starting back down to 1739, 443, for the registers, so we have gone down a bit, tiny bit. I keep doing that. Keep pushing compile when I want to send it to my FPGA anyway. That's cool. Uno Noctium. Yeah, I'm just gonna force push this stuff too. I guess as soon as you add a lot of those other features, Grey Bush, then it's really explodes the scope because a lot of those are cross-cutting concerns. Anyway, we finally got our register file. That's pretty nice. That was one of the things I wanted to look at today. The other was simplifying these unaligned reads and writes. Loads and stores, I should say. I'm not doing those very well yet. But I also didn't want to stream for 3 hours today. So I think I'll cut off the stream today. I'll probably stream a lot of this tomorrow too. But yeah. Yeah, I think I'll head out for now. Anyway, thanks for all the help, guys. It was a frustrating day, but not because of you guys. Frustrating day, but we got to where we wanted to. If nothing else, we made progress, so that's actually pretty nice. Streams happen, exactly. All right, see you later, guys.